Hello, everybody, and welcome to Google Cloud Next 2017. It is great to have you with us here today. My name is Mike Procopio. I'm a software engineer on the Google Drive team, and it's my great pleasure to talk with you today about a feature that we recently launched called Quick Access for Google Drive. And we'll use Quick Access as kind of a way to pivot and learn a little bit about how we use machine learning at scale at Google and also on Drive, and sort of take a tour through some of the challenges associated with bringing in an intelligent feature like Quick Access to Drive. A fairly casual session here today. There'll be a demo, time for Q&A later, and so happy to stick around and chat with anybody about those things. So, first slide here is a preview of our talk. Now, some say that agenda slides are no longer allowed or they're not in vogue anymore, so this is definitely not an agenda slide. However, we may cover some of the things listed in the bullet points here today. As you see, it'll be more than just specifically about Quick Access. We'll be talking a little bit about intelligence features in general, and also take kind of a closer look at some of the production engineering required to pull off a feature like this, because it is a bit of a feat. Look at some of the metrics and dashboards that we use to evaluate it. So a few of the challenges that we've had along the way, look at experiment frameworks and a few case studies that we went through in order to kind of get the feature up to snuff and the quality high enough. If things go well, we might even have a demo, and then finally we'll have time for some Q&A at the end. So, intelligence in Drive. So as a kid growing up in Florida, my experience was watching the space shuttle launch, which was awesome, and I quickly became aware that space was hard. Right? And I think about that a lot, especially as we've done increasingly intelligent things at Google. And something that I say to myself often is that intelligence is hard. Now, that doesn't mean that it's a miracle. It can be done, but these things are often unforgiving and complicated. Fundamentals of machine learning are also complicated, like spaceflight. Machine learning is easily misapplied. It's very easy to think that you're actually helping the user when you're not. 20 years ago, I can remember an assistive experience in a productivity suite wherein I would be starting to type a letter, and then an assistant would try and help me with writing a letter. That's an example of an earlier kind of experience, but yet I've got nothing but love for the early days of assistive features because of launch and iterate, and we have to start somewhere. Similarly, with Quick Access and intelligent features at Google. So doing easy things with machine learning, as we've seen in the past decades, is easy. Doing useful things is a little bit harder. And so how do we get there? Well, we start small but real. We measure, we're rigorous, and we always make sure that we're helping. Having a compelling UX is very important. And at last, we can launch and iterate and never lose sight of what we're here for, which is the user. Focusing on the user and increasingly focusing on the business is part of our DNA. We're here to help people do their job better, not just build some shiny, fancy thing. We're here to help the business run better and to create value. And that means more and more tackling exceptionally difficult problems, making our lives, more challenging and more difficult, if you will, in the name of the user, in order to provide experiences that help them do their job better and to provide value to the business. This is a pretty extraordinary opportunity. If you look at it, an organization's entire knowledge is stored in Drive in the cloud. It's a massive opportunity to do intelligent things. The data is there. And that relates to one of our goals, which is to increasingly evolve Drive into a center for knowledge exchange for your business. And that is quite a lofty goal. It's more of a mission or a vision. And how do we get there? Once again, we return to our first principles, which is launch and iterate and always focus on the user. Today, we launched Quick Access for Team Drives, and later last year, we launched Quick Access for enterprises in the My Drive space outside of Team Drives. That's our first big feature in this space, and if you think about it, represents a launch and iteration of its own. Let's take a quick look at Quick Access. So fundamentally, the value and the premise of what Quick Access is trying to do is very prominently display documents to the user that they're likely to want to open. These could be documents they know about. They could be documents that they don't know about. We want to ultimately allow them to make better business decisions, showing them relevant documents to help them make the best decisions they can, adding value to the business. And as a secondary goal, and this one's a little bit easier to measure, we ultimately want to save users time. And our early data show that quick access, when you open Drive and your intent is to actually open a file, when you use quick access, you get to your file 50% faster. That's because regardless of whether you have folders and are an organizer, if you will, or have never created a folder in a storage system in your life and rely on search, quick access is going to show you the most critical files that you're most likely to open at that period of time. And our data show that we've been fortunate to have a lot of success here. A quick tour of what we're talking about. So quick access is available on all platforms. And for Drive, that's mobile and web, Mac and PC. Quick access not available on the Sync client, but on both iOS and Android. Here's what it looks like on Android. And importantly, as of today, this is now rolling out to Team Drives as well. And that's the screenshot on the right. Similarly for iOS, both My Drive and Team Drives. And also rolling out over the next 2 weeks, we have quick access for the web. And we'll actually be demoing that today. And there's a live demo downstairs as well, I believe, in here or in Moscone. Also rolling out for Team Drives. So this is fairly important for us. It's not something you want to build for an individual platform. Platform parity is important. We want to make sure when we build a feature that it works both for consumers and their My Drive, but increasingly in enterprises and the recently announced this morning Team Drives, and that is a key goal of ours. Kind of an early look at some of the impact that we've had. We're fortunate to have success with this feature. One of the happy thoughts here is that intelligence works. We can do useful things with machine learning beyond just toy problems, right? We always have a baseline that we evaluate our approach against, and our data show that we are beating the baseline, in this case, MRU, or most recently used, by a statistically significant amount in all cases. So that's great. We've also seen that quick access saves users time, reduces time to open a document by 50%, assuming you're going to Drive to open a document. And then more subtly, quick access has really proven out our machine learning infrastructure here on Drive and given us a solid platform and framing to iterate more quickly to do other features. Because there's so much that goes behind it, including all of the production engineering and all of the measurement rigor and the dashboards, and even some of the cultural mindset that we'll dive into here in a moment. Let's take a look at the production system. So this is a large-scale production system, and one of the early findings here is that a machine learning project is not just like we're going to go do machine learning. We don't do it in a vacuum. Instead, it exists as part of a much larger production system. And when you're talking about the recently announced 800 million monthly active people who use Drive, thousands of businesses across all of the platforms that we've just seen, this is a large-scale production system. We have to have rigor around the servers, all the data processing pipelines. Even the UX must be very carefully thought of. Dozens of servers are involved, and it is a Google-scale project end-to-end, which means it's hard but very exciting. It takes a lot of infrastructure to get here. Some examples are on the right, and I just kind of put together this list. So it's the machine learning frameworks and toolkits that you would expect: Google Brain, Distbelief, which is our internal toolkit that we use right now, increasingly in the future, TensorFlow, which is our open source machine learning framework. All of the data processing, large-scale analytics that we use with parallel processing on the back end via MapReduce, which is kind of our core distributed computational technology. An experiment framework to be able to evaluate hypotheses to figure out whether you're actually improving the system. The ability to query large-scale data, all the stuff you need to stand up servers in multiple data centers, load balancing, deployment, APIs, and the remote procedure calls that you make in between them. All of the dashboard visualizations, and finally, a framework to be able to do statistics well, because doing statistics well, it turns out to be very difficult. Here's an architecture diagram. We won't go too deeply into this, but the general idea here is that to be able to predict something like this, you'll find that there are a lot of pieces here. In this case, there's the offline model training. We're training up a neural network. That's an offline process that takes 1 or 2 days. We'll see that here in a moment. And then the evaluation is done online or in real time when a client makes a call to generate the most probable documents that you want to show. But on top of this is all of the metrics and the logging and the dashboards and the experiment framework. And then very critically, there is a dedicated service and team that is actually responsible for aggregating and anonymizing and generating the data that is ultimately used to train models and indeed extract features that are used when we're making predictions. That's activity service in the middle. So turns out the actual science, the machine learning aspect of it, is one comparatively small part of a much larger production system. It's an exciting result, but it means we have to really focus on what we call the prod eng as well. So one thing we'll do today is learn about the actual machine learning that we do here at Google, and in particular for this. Machine learning in general requires three broad things: features, data, and algorithms. So features are basically the signals that you can use to kind of separate data and to make predictions. In other domains, they're called inputs or predictors. Multiple features together, these are signals extracted from, this case, documents. Multiple features together form a feature vector, where a feature vector can have a lot of different features, in this case, tens of thousands in this particular project. Some of those features are raw data, some of them are engineered. They're functions of other features. We apply certain transformations. In general, we do fairly minimal post-processing, not too much scaling or anything like that. The neural networks are very adaptive to kind of take anything that you want to throw at them. And some examples of features that we would use here include per document item counts of the number of times a document is opened, when it was last opened, these kinds of things. The time or the temporal aspect turns out to be a very predictive and powerful feature. And so we encode this as periodicity. And what that means is, if you open a document, and this is an example of a feature that we found to be very compelling, if you open a document every Saturday morning, maybe your household budget at 8 a.m. over your coffee, and you do that every Saturday at 8 a.m., well, that is actually very strongly predictive of you probably doing that next Saturday as well. Great opportunity to save you time so you don't have to drill down into your folders or search. So if we can encode that correctly with a little bit of feature engineering, we have on our hands a very powerful feature, which overall is part of the impact of the intelligence here. So we also have user models. We understand a little bit about the user and the things that they do, their actual behaviors, not conditioned or on an aspect of any specific document, but about the user themselves. And those turn out to be useful signals for the model. And then finally, in the future, and we'll nudge against this here shortly, but there's a lot that we can do here that requires a little bit deeper understanding beyond just documents, but for example, the user's social graph. For example, if my boss has been commenting on a file that I'm working on, is probably more impactful to me than somebody further in my network. And right, so we want to capture this mathematically in terms of the statistics and the model prediction and factor them in. So the features are ultimately extracted on raw data that is, in this case, produced from an existing service at Google called Activity Service, which receives and records events on a per document level, which for the scale that we operate at Google is no small feat. Things like when the document was created and shared, opened, when it was commented on, all of the things that are available, metadata about the document that we want to encode. There's also user stats, basically the user model that can be computed offline, attributes about the user, and then in the future, other deeper understanding around the social graph. So per document activity and offline user modeling and processing is the fundamental source of most of this data. And at last, we come up with the algorithm, which has historically been, as a machine learning practitioner, one of my favorite things to talk about, except at Google, it's just really boring now because we just say, okay, everything's a deep neural network, right? And once upon a time, neural nets were very much not in vogue, positioned to other things you may have heard about, like support vector machines, large ensembles of simple linear classifiers, for example. But with the advent of backpropagation for training, they sort of come into vogue. And as it turns out, the only thing that matters is how well the actual algorithm does in practice. And what we find is that neural networks are extremely capable in this space for a large variety of problems: searching, ranking, prediction, image classification, for example. And they are very robust to large numbers of features, like in the tens of thousands of features. If you did that something, for like a support vector machine where the training complexity is a function of the number of features, well, the model might not ever converge, and you'd have a not effective classifier. So neural nets kind of take dimensionality out of the question, which is very exciting. And internally, we use dist belief, which is described in the literature, internal to Google, but soon we'll be moving to TensorFlow, which is the open source machine learning toolkit that's very powerful. It's great. It means that that people outside of Google can use the exact same technologies that we use for prediction here, including for our searching and ranking tasks across Google. Neural networks can be wide or deep. Ours are not particularly deep. I think there's 5 hidden layers between the inputs, right, for each feature, and then the outputs. And I think 80 on the order of 80 nodes per hidden layer. So it's a fairly wide, not super deep neural net, which is not at all uncommon. Okay. This is fairly technical talk, and you wanted details. This is a quick slide to talk about specific details that we actually use. As we've seen, this is modeled as a neural net trained with what we do typically now with conventional backpropagation, and training uses asynchronous stochastic gradient descent in particular, as described in the literature. We use 40,000 features right now. That's a lot of features. We probably don't need that many. We suspect we can do just as well with our predictions for quick access with fewer features. Feature selection is a little bit difficult for a neural network, as is interpreting the model, but we're going to work towards that. This is set up as ultimately a 2-class classification problem. The probability that you're going to open this document right now, or not that, right, and on a continuous output, which is the output of the neural net, and kind of separate out the boundary and rank as desired. And so you need positive training examples of things that the user has opened in the past, and then negative training examples, things that the user has not opened. So that forms the basis of our classification. Training is a very large task. Right? We have a lot of features. It may take 1 or 2 days for the actual model, and we're generating one model to evolve and to converge. And there's lots of cross-validation and creating multiple replicas, and it's a very computationally intensive task distributed across, I think, a couple of hundred individual processors, workers in this case. So this is a fairly large endeavor. But of course, we do all of that work, which is basically pre-computation. Why? So we can evaluate quickly in real time, right? When a user opens up, when we open up Drive, we see quick access. That is a real-time request to get the most probable documents for the user in that moment based on the state of all of their documents. And that means we're extracting the features in real time, and we can do that on the order of 100 milliseconds in the common case. So we do all that work training to be able to come up with a very quickly evaluated model, which is one of the benefits of a neural network model. So good. So taking a step back from the details, I wanted to get a little bit philosophical. I've been thinking about this a lot. One of my favorite things about Google is this increasing machine learning aware culture that we have here. Now, when I first started, it was, we used machine learning in like search, for example, but did not have this cultural presence that it does now. Times were different, and it's what I went to school for. To see it kind of take hold is very exciting. But it's not just individual engineering competencies; it's everything that it takes to land a feature like this that we have at Google. So the concept of having privacy front and center, and thinking about that, and talking candidly about it, and having privacy experts who are aware of common concerns that we could have, a very privacy-centric culture is critical to doing this project properly. Cloud expertise. This is a cloud project. We're not operating on local data on a filer, right? So we need to be very good about processing data in the cloud, doing that in a thoughtful way. And it takes leadership buy-in, right? This is not just an individual engineer's project. This is a large endeavor. The whole concept of intelligence features and assisting the user, very important to have leadership buy-in all the way down from team leads to engineering managers to executives, right? To kind of transform the culture and to support a project like this, because it's fairly expensive in terms of how many people need to support it and the research that we've done. Of course, we've seen all the systems infrastructure that's required. Product managers need to be bought into the value proposition to the users and need to be shown that we're actually helping users. There needs to be an enterprise focus increasingly, because that's where we see most of the impact from features like this. We need to do the UI and the UX very well, because we can do harm here, right? If we surface a great feature that doesn't have a compelling UX, we'll see some screenshots of this here shortly. And just in general, broader culture around learning and intelligence, and having classes that people can take just because, and learning about statistics, and being able to increasingly just think, how can we do this kind of naive thing maybe a little more intelligently? So I've really come to appreciate the increasing machine learning culture at Google, and I have seen that is really required to be able to pull off a feature like this. So, So we've seen how we can use machine learning to generate models. One of the most important things that we can do is measure our success. Measurement is critical for any project like this. My dad used to tell me, measure twice, cut once. I didn't always obey that, but I definitely do now. Our approach is basically threefold. We define rigorous metrics that are meaningful, right? These are numbers that you can actually use, optimize a model to. It's a very mathematical thing, right? A loss function or an optimization function. So we define these summary metrics ultimately to capture what we think the user cares about. Right? How often we're predicting the right sort of thing, how often they're engaging with quick access in general. They have to be carefully defined. And then you can't just report a number. You need to do proper statistics around them. And if you're comparing different sorts of approaches in an experimental fashion, you need to be able to compute confidence intervals on the test group versus the control group to figure out if you've actually helped or hurt. And then finally, it's very important to have a sensible baseline. In this case, we're going to predict your most recently used documents as a baseline, things you most recently opened or edited, and we want to do better than that. If we're not doing better than our baseline, we're not really doing an intelligent, impactful thing. Specific metrics that we use, that we care about, and they all capture different things. First, the astute viewer will note that all are going upwards and towards the right. That's a very good thing. So I wouldn't call them fully hockey stick, but they're trending in the correct direction. That's not an accident. We want to rigorously improve this continually, and only through doing that will we land at a useful thing. Examples of the three metrics we use: hit rate measures the actual percentage of the time that quick access was correctly used to predict the doc that the user went. In other words, the percentage of the time that the user found their document through quick access, which is subtly different than accuracy, which is more the percentage of the time that quick access predicted the document that the user ultimately did open. Right, see the nuance there. And then finally, click-through rate, which is more a measure of engagement with the UI feature itself. What percentage of the time are the users actually using quick access when quick access is available? These don't paint the identical picture. It is possible to optimize for one of these but not the other, and now we have a problem, right? So we consider all three of these metrics together, and we want to see them improve together, having seen firsthand that it's possible to improve one and not the other. Similarly, we have production metrics. There's a lot of dependencies. This is not a science project. We are constantly monitoring the health of what we consider to be a service. The three key things there are QPS, queries per second; latency, in other words, how fast are we doing this, where fast is a very important thing to do things in, as well as error rate, right? We want this to be a reliable, error-free experience. Examples of what this looks like, and we track them. QPS is on the left. You can see kind of our natural cycle. We do have a daily cycle. There is peak traffic at a specific time during the day. This is the challenge of any production system, is coping with peak load, where in general we try and smooth things out to the extent possible. We've done some load testing, and of course there's organic platform growth. We're rolling out to other platforms, and additional users are coming to those platforms, and that will be reflected in that. Similarly, we always compare QPS with latency, because there is a relationship here that the more you throw at your servers, the more queries, on average, the slower things are going to get, especially if you have to queue requests or there's other capacity issues. We've made some major strides with our latency, and we look at things like latency in the average case. But how about latency like in the worst case? Maybe you have a particularly large corpus or a large number of files, right? So we never look at these numbers in isolation. We talk about things like median latency and latency at the 95th percentile, for example. So we've done some optimizations here, launch and iterate, right? Always optimizing, finding the bottleneck. Parallelization solves a lot of problems, as well as just throwing more hardware at things, right? If you're under-provisioned and slow, well, maybe add a few more tasks or instances of the server that can receive these requests. Pivoting to dashboards, this is one of my favorite aspects about this project. It would be very easy to do something like this and have ad hoc analyses on running one-off queries by one or two people, but instead we've institutionalized the things that we care about. We've done that through a dashboard, which is critical infrastructure in its own right. They show real-time results of the system. They show the results of the experiments that we're trying to do. Here we've scrubbed the numbers because they're sensitive, but you can see our three key metrics are there, but also the confidence intervals, and then the comparison with our baseline. So it helps us to kind of get cultural knowledge around how well we're doing, and of course they're very transparent. Everything is transparent here. And critically, this is always based on heavily aggregated, anonymized summary statistics data, very critical for dashboards. Other examples from the dashboards, we have our historical primary metrics over time, both in graph, time series format, and in tabular format, as well as how much time we've saved the user. That's very important to us, and we can actually chart that as kind of an area under the curve sort of a thing. Positional statistics count. This is an interesting finding. We find that the majority of impact that comes from this is going to be in the first n predictions, right? And so if all of your data, if all of the benefit of your feature comes from predicting just 3 things, and you're getting it right so much that you don't need to predict the other things, well, the other 7 things, or have an extended carousel, you can imagine that that's important for UI and UX. In particular, maybe our carousel doesn't need to have 10 items in it if we're always or usually right at the first 3 or 5 things. So these dashboards, this data feeds back into a number of decisions. 3 challenges that were particularly, and by challenging, I don't mean unpleasant or difficult. I mean intriguing and very engaging. Right? It's the challenging stuff that makes for a good, an exciting engineering day. Privacy is perhaps our most critical challenge, but it's also built into our culture. And so it's this wonderful dialogue that we continually have about every time we code or do a design review, we're constantly poking holes in things to say, could that data leak? Or do we need to aggregate that data? The answer is yes. Do we need to have you anonymize this data? We're very careful with log sources, these sorts of things. We think about this cross-functionally, not just engineers, not just leaders, but product managers and program managers. It's always on our mind. And importantly, there are experts who see these things all day, every day, and understand the common modes or areas of concern that we might have around privacy, both in different usage modalities, for example, enterprise versus consumer users outside of the enterprise. It's a passion, and it is an interesting problem in its own right. Right? We understand that we have very important constraints that we have on the data. We need to do right by the user, and we need to be very careful. And so how can we make experiments around hypotheses based on aggregated data? How can we still build a useful system with these very careful controls in place? It's a science problem in its own right. So a couple specific things: we don't allow raw access on the engineers to any kind of user data. We don't allow user tracking. Instead, we work with anonymized data and aggregated summary statistics. And as noted, enterprise data is specifically not available for use in most cases. Another challenge is the challenge around data quality. Right, so we have an existing server that was first built to generate document data, and this is a fairly old screenshot, but to generate activity data for a given document in the Drive clients, in the UIs. And that is a very different task than generating data that's going to be used by a machine learning system for a neural network that's saying, feed me features all the time. So that's actually one of our challenges, is it's very fortunate that we have this infrastructure, but it's a new use case for an existing service. That means there might be holes in the data, or that we may need to process some of the data more. Not all the things that we need are there. And of course, ultimately, we just hooked up a very large-scale system to an existing server that needs to be very carefully provisioned for that around rollouts. So data quality, availability, server load is one of these kind of classic production engineering challenges that we have. And then finally, pivoting towards UI and UX, it is not easy to create a useful UI here. And part of the challenge is that as your predictions get better and better, you may be able to finally land a different UI. You may be able to have a more prominent UI. Maybe it's shown all the time, only once your predictions get good enough. At first, we weren't sure, right? And we would pop up, as you see on the left, a modal dialog only when our predictions were above a very high confidence, right? Well, because they weren't always. We hadn't launched and we hadn't iterated enough. But over time, we got better. And we are in an era of where we have user UX design and UX research. And just like we run experiments on our hypotheses for ideas around features for our intelligence, so too do we do research around how a given UI looks. So we have a very strong culture around prototype and doing user studies and iterating. And at last, we ended up on the UI that you can see here today on your mobile device on iOS or Android, which is the one on the right. And even then, we're iterating, as you'll see in a few more screenshots, to where we'll talk about that, to a more different design showing larger thumbnails. Experiments are a critical part of of the way that we are able to improve the overall system. In general, it is very easy to say, hey, you have an idea, let's make a new feature and put it out there, and you have no way to know if it helped it. Certainly, you could drum up a use case that shows, hey, look at this, I did this thing, and now this new thing is being predicted, and it's perfect. But maybe you made it worse for everybody. And in fact, you probably did, because improving a system like this is not a trivial thing. And features that you think may be useful for you may not be. And yet, this kind of creative hypothesis generation is at the center of how we can potentially improve things. This is science, basically. It's a science experiment. So we have a very rigorous kind of cultural cultural use of the experiment framework, which is part of our common infrastructure at Google. So we can rigorously test the hypothesis and figure out whether we're actually improving or hurting. And over time, the model accuracy improves, and we hope the user adoption does as well. A few case studies here to look at how this works. We encode how recently an item is opened or edited, and we're trying to figure out how best to represent that. In other words, we're actually trying to figure out how to engineer the raw data into a feature that the neural network will most effectively be able to use, optimizing ultimately for your summary metrics. So the hypothesis here is that opening or editing something within 1 or 5 or 10 minutes, basically showing a histogram of counts of the number of times it was done there could be useful. But there's so many free parameters here, right? Basically the bucket size of the histogram, which is a very common way to represent feature vectors for machine learning algorithms. So we run an experiment, right? Multiple experiments to figure out what will the model best be able to predict with. And ultimately we found that encoding a feature and bucket size that captures the fact that a file has been acted on at 1 and 5 minute intervals was impactful. And the result is we correctly chose the histogram of bucketing size to be able to give our model the effective feature representation to be able to make good predictions. You can see how nuanced this is, right? We wouldn't be able to just do this arbitrarily, and it was only through statistically significant experiments that we can find that, hey, we did well here. Another case study is using calendar data. So there's a magic moment here, which is basically you have a meeting coming up and somebody's attached an attachment to the meeting of something that you need to go over ahead of the meeting or during the meeting, right? So you don't want to be chatting links to the thing. Everybody needs to have the agenda pulled up on their document or whatever, on their laptop. And the idea is that, hey, we think we can do a cool thing here. But we have a little bit of humility to know that maybe it's not always the right thing. We also need to understand we have to figure out how to we have to figure out when to show this, right? So if I show you a document that is going to be in a meeting 2 weeks from now, that's not going to be impactful. That might actually hurt our overall, statistics, the overall metrics. Maybe we could have predicted something better in that first slot, for example. So we're trying to optimize here. So what was our finding? We were able to find values for when to show a calendar attachment in the first slot that overall had an improvement to our metrics and that had an acceptable click-through rate for that prediction. And we'll actually do, the hope is to be able to do a demo of that here now. Demo time. Okay. So my friends always ask me, why do you do live demos and talks like this? It's because I like to live dangerously, said with an English accent that I'm not able to do. And then my boss, who's in the room, always asks what could possibly go wrong, and that's just something that we say here. So nonetheless, we're going to do a demo today to kind of show what quick access looks like on web, which is, again, rolling out in the next couple of weeks, and also look at what quick access looks like for team drives, and we'll use the calendar attachment as our approach. So looks like we've got the demo up there. So in this demo, there are 2 accounts. There is somebody in the if I move over here, in the Inc42, which is a test domain, it's a domain that we have here at Next, which is basically modeling an enterprise. And you can see I have quick access predictions here. I will shift reload and see what we get. People are using this, so the predictions are so somebody just created some meeting notes, great, so that's showing up. So there is an existing appointment on this person's calendar, presentation on ML, that's right here. And that appointment is shared with this second account, which is in this window right here. And so the idea is that we're going to come here, and this is the user that's not in that enterprise. It's actually a personal user. And they will make an attachment to their to the calendar appointment shared between the 2 users. In this case, I'll click on this. You're invited to the reunion. Maybe they've got a little family reunion thing going on. Save it. We'll send out updates. So that's going to write and propagate into all the systems. So if I come back into Drive for this user now that was in the domain that has a shared calendar appointment that just had an attachment added to it, and they happen to go to their Drive, the expectation is that they will see that show up there. There it is. Yeah. Okay. Oh, you all. All right, I'll keep doing live demos as long as they keep working every time. Okay, right. So that's great. There are other things I could remove it. It would show up if I removed access for this user. Everything is live and connected. So if I removed access, it would remove itself automatically from that list. While we're here, we can drill in and take a look at what quick access looks like for team drives. There's a sales team test team drive here. You can see that we actually can make quick access document predictions within the context of a team drive, very enterprise focused, and that's rolling out in the next few weeks. Of course, team drives just launched today. We are finding early results that show very compelling data that these predictions are especially useful in the context of team drives. The problem is it seems very applicable to machine learning, so we're able to have pretty high results and statistics on our predictions here. So that's super exciting and also very motivating to continue to iterate here. So that's it for the demo. We have a few more slides to kind of wrap up and talk about future direction that we can switch back to here when you have a chance. Thank you. Future directions. Quick access is only the beginning, and as we've had success with this, it's very encouraging to have these early successes, but we have a lot more that we want to do. So here's an idea of what we can do both with quick access and beyond. Of course, at Google, we have a saying, fast is everybody's favorite feature. You have to be fast, right? It's called quick access. You don't want to wait 2 to 3 seconds for your documents to show up. You want to wait 200 or 300 milliseconds for your documents to show up. So there are things that we can do here. We can have a cache where we maintain the predictions, and then when the predictions might change from the backends because the underlying data changed, we can push basically a notification in the cache that says you need a refresh. We'll do the polling offline, and then we can answer this in tens of milliseconds, for example. Caching, of course, known to be the solution to all known computer science problems, but also the cause of all known bugs in production systems. So we have to be careful with our caching. And we'll probably have an experiment with the cache on or off. The hope is that faster results will improve accuracy, but we don't know that. So we certainly hope it does. Also, client-server protocol optimizations, always leaning out the message size back and forth, leaning out the number of server calls that it takes to actually get this data. We want increased quality as well. In general, we can make small tweaks to the model parameters and run our experiments, but we feel right now that the majority of the larger increases within the context of this specific quick access feature would come from using new signals. Right, signals from across G Suite. So, for example, the social graph, weighting things by people who are in your network, your professional network, closer, weighting those more heavily, and then also understanding maybe even the organization hierarchy. And then there's also the concept of topical information about a document, wherein you're probably, on a general basis, more interested in documents that are about things that you have previously read in general. So we can extract a topic model and then do computations as well. So new signals, we hypothesize, will greatly increase the quality of the quick access predictions even further beyond the baseline than it is now. Of course, this is an infrastructure project. We are always having infrastructure efforts. We're improving our servers. We're improving reliability. We're adding capacity. We're migrating, in this case, to TensorFlow, which is Google's open source new generation machine learning toolkit. And then finally, new features, and by features I don't mean machine learning features in the sense, I mean user experiences. So we've just launched Team Drives today. It represents a very substantial 1 to 2 year long effort. There's a lot of opportunity here. We think that there's so much value around intelligence and assistive UIs in the enterprise space, especially in the team space, that we've already started envisioning a lot of impactful features here beyond just things like document prediction. Deeper understanding and assistance with content and file organization. Some people have a very carefully curated file hierarchy or folder hierarchy, but not everybody. In fact, it's not even necessarily that common, and curating data takes a lot of our brain cycles. We feel that we can probably automate this task pretty well, but that's just an example of another feature that's somewhat different than quick access, and yet would have the exact same kind of approach, right, around the production infrastructure, the feature generation, the use of a neural net, perhaps, and then the dashboards and measurement rigor. And then finally, if you've seen quick access here, you've seen that the little carousel was kind of placed in at the top of the UI, right? The predictions are good enough, and we're saving enough time that we feel like we're able to give a fairly high prominent UI experience with the prediction carousel. However, we're starting to envision other things here around people and teams that are harder to fit into existing UIs, right? At some point, we've kind of shoehorned everything in. So we're starting to imagine a completely different experience that kind of moves us past a raw listing of files and more towards kind of a more holistic intelligence and assistive experience. So that's coming soon. Some key takeaways. To do well here, everything has to go right. Right? If you have to get the correct signals for your model, you have to train the model correctly. You have to optimize the model to the correct metrics, right? That's a mathematical process. You have to optimize for that. You need good infrastructure that can scale to 800 million users, across 4 or 5 different platforms, hammering this endpoint, requesting their predictions. You need a beautiful and very usable user experience, or otherwise you're going to get in the user's way. It all has to be super fast, and you have to continually improve with new features and new signals, and do that in a principled way using experiments. And if you do all of those things, and it is an and, then what we have found is with this dedication, we can slowly improve the quality of our predictions to where we're doing a useful thing and it's no longer a toy. And that is what we've launched here today. And we think it's quite magical, an intelligence feature that delivers real value to the user and to the business. And then finally, I wanted to leave us with some key ideas here. Intelligence features like quick access add value to the business. They enable users to make better decisions, and we've seen that it saves them time. We've seen that I like to say that intelligence is hard, and yet it can be done with a very rigorous approach. You need a lot of infrastructure and expertise, and also a culture around leadership and product vision, and a dedication to launching and iterating continuous improvement, the experiment framework, and rigor. We've seen that a compelling UX is critical, right? I can dream up a lot of very fancy things that a neural network could predict and have no idea how to surface them in the UI. Other things that we could possibly predict, and I wouldn't know how to do that. Or you could do that, it would be modal, and now you're interrupting the user. Compelling UX is critical, regardless of how good your neural network accuracy or area under the curve is. These things are very closely related. And then finally, quick access is a large-scale infrastructure project. It's very much about production engineering. It's not just about machine learning or even TensorFlow or the machine learning toolkits. It's all the servers. And then at last, it's something that's truly native to the cloud. Having the data in the cloud is how we can do this. It's not something that you can do on the filers and impact users in a positive way like this. And one of my favorite things that I've seen about Google is we have the resources and leadership buy-in, and there are machine learning experts who come to Google, and we built out our cloud infrastructure, all to the point where at last we can deliver something like this, and it is truly exhilarating. There is much more to come, and I'm grateful to be a part of it here with you. Alrighty, everyone. Thank you very much for your attention. I appreciate it.